Welcome everyone. Welcome to the week 7 of our reading group. I'm Shixuan Liu, and today I'm going to present with Qirun on some topics beyond the scope of training data attribution, which is the factual knowledge attribution. So let's get started. For the first part, I'm going to present just 3 papers on this topic. One is a survey on the large language model attribution, and the other one is a paper that provides a unified framework for 2 kinds of attribution, the corroborative one and the contributive one. And finally, I will lead you to take a look at an interesting paper that showcase an application of training data attribution on some probing stuff. This is today's outline for my part. And okay, for the first paper, we'll cover the overview of the large language model attribution here. And I will also describe in detail some different approach to attribution. And finally, we'll discuss about some limitations, challenges, or future directions for large language model attribution. So the task of large language model attribution actually is one kind of factual knowledge attribution. The main task of this kind of attribution is to generate some evidences for the generated content of your large language model. And why do we need this kind of attribution? Because today for modern large language models, correctness is not everything. We also need something like the groundedness so that we can convince people, right? So that's why we have the large language model attribution here. And there are actually 2 essential requirements for large language model attribution or good large language model attribution. So the first one requirement is the high recall, which means the attribution should be comprehensive. Let's suppose your large language model made like 10 statements, and what you want is that you could have 10 corresponding evidence that backs up the content generated by your model, and you don't want to leave out any one of them, right? And that's about the recall. And as a pair of metric, the precision just states that your attribution should be sufficient, which means your retrieved content should be to the point or relevant to your claim. There are actually also 2 different sources of attribution. The first kind of source is just the training data. So in this context, it actually large language model attribution has a lot to do, or at least some overlapping with the training data attribution. When we are doing some training data attribution, actually we are focusing on the trustworthiness of the model because we want to trace back to the training data and explain the model's behavior in a specific task. And on the contrary, we also have another source of attribution, which is the out of model knowledge. If we are doing some out of model knowledge attribution, actually we are seeing the potential of improving the capabilities of our large language model because we want to empower our models with some more accurate or up-to-date information from any sources. Okay, so here is actually the most important part of this paper, I think. So I'm going to introduce basically 3 different approaches to do large language model attribution. These 3 approaches are the direct generated attribution, the post-retrieval answering, and the post-generation attribution. And here, this diagram here just shows some examples, but I'll just go into details one by one with you. So the first one kind of attribution is just the direct generated attribution, which is very simple and intuitive. It is just asking your large language model itself to do some detection and attribution. It is taking a second look at its generated content generated content and see if there are any flaws and also provide some evidence for it. So, and one drawback of this kind of attribution method is also very obvious because, large language models themselves could hallucinate, right? So if your attribution contents are also hallucinated, then that will not be so convincing. But nevertheless, there are some examples for this kind of attribution method. So here are the such as the recite the blueprint model here, and I just want to show maybe one example for you, which is the recite model, recite method. So recite stands for recitation augmented large language model. And actually, it looks very similar to something called the RAG, the retrieval augmented generation. And they have some subtle differences. So for the recitation augmented generation, actually, instead of retrieving something from outside the source, it is actually asking the model to look up its own memory. It is telling the model to generate some recitation in the first place before it do any answering. So actually, this paper also involves a lot of engineering techniques, just such as major voting ensembling or maybe multi-hop recitation, stuff like that. But I think the key point in this paper is just do the recitation before generation of the model. And another approach to attribute is the post-retrieval answering. I think it is more familiar to everyone because RAG, the retrieval augmented generation, is just one classical example of this type of attribution. It is using some information retrieval mechanism to retrieve something and ask the model to answer based on the retrieved data. And some examples are the seer chain or max line. And I'll also showcase one example here. So the seer chain is searching the chain. It is a kind of post-retrieval generation. The chain here stands for the COQ, the chain of queries. So the chain of queries basically is also something similar to chain of thought. It is asking the model to generate a series of queries that could guide itself towards the final answer of the question. And so the searching here just is recursively applying this technique. So as you can see in the diagram here, so for the first round, this algorithm just asks the large language model to generate one such COQ. And after that, you will have an information retriever to process along this chain and until it has some problems. The problems could be anything, such as it couldn't search anything, or maybe some further detection by the large language models are still required. And if such case happens, we'll just call the large language model again and generate another COQ in another direction. So by recursively calling this kind of mechanism, we'll finally has a branch that passes through to the final answer. And based on the retrieved stuff, we can ask our large language model to generate some more reliable answers. The third kind of attribution approach here is just the post-generation attribution. And this type of attribution method is actually focusing more on the verification or the modification of some generated contents. And this diagram here basically show the framework of this kind of attribution. And I also have some examples here, the RAR, and I want to just use the RAR as an example. Basically, you'll have one text generation model here, and you are you have an input pass to this model, and you are getting an output, right? So the novel point here is that the process will do some research and revision on the generated content. Basically, the authors implemented a technique called the comprehensive query generation. And it asks the large language model to take a second look at the content it generated and ask a few questions about it. So these questions could verify whether the facts are correct or not. So with these questions, we can use some information retrieval mechanism to retrieve some kind of the report here. And based on the retrieved stuff, we could just revise our output accordingly. And finally, they also have some evaluation process, either by human or automatic process, and give some scores for the revised output and the attributions report. So these are the three main types of attribution. And we also have one additional way to attribute here. It is called the attribution system. And it is something more comprehensive, and it may just contain one or more techniques we just discussed before. And it may also involve some explicit training or fine-tuning for some kind of models. Here I want to use a model called WebGPT as an example. So basically, the main contribution of this paper is that they have developed a text-based web browsing environment for any kind of for any kind of language models. And they just use some kind of techniques like RLHF to fine-tune their models to teach them to interact with such an environment, so that the environment so the model can further be fine-tuned to answer some long-form question and answer downstream task. Yeah. Okay, so these are the main contents, I think, for this paper. So are there any questions from the audience? If no, I'll just proceed. So finally, we are going to discuss about some limitation and also maybe few potential future directions for large language model attribution. So actually, there are a few challenges or limitations for current attribution method. The first one is the outdatedness, which means your things, the information, some information are just get updated from time to time. So your attribution could easily become outdated. One potential direction to solve this problem is just to refresh your large language model to continuously. You can either refresh the memory of your large language model, or maybe just refresh the source of attribution it is accessing. And another limitation is actually the inaccuracy and bias of the attribution. Sometimes, the large language model may link the content of may link the content to some incorrect sources, or maybe when it is selecting sources, it may be biased and lean towards some kind of information but ignore others. So this kind of problem actually is very misleading for people who use the large language model, because it could just hallucinate something and say it is generated by some very trustworthy source, which may cause some very serious error. And one potential way to solve this problem is to enhance the reliability of their outputs. By this, I mean, we could just teach the models to distinguish from which sources are more reliable or which kind of sources are not, and do some training on it, and it could mitigate this kind of problem. And finally, it is the problem is lies in the excessive attribution, because simply the models just don't know when and how to attribute. And when this kind of problem happens, it will just make the generation of the model become inconsistent, because it just sometimes comes up with attributions that very abruptly, right? So another potential direction for solving this problem is just to balance creativity with proper credit attribution. Uh, so I think this is all about the first paper. And since like we don't have a lot of questions, I will just directly proceed to the second paper, which is called the Unifying Corroborative and Contributive Attributions. So in this paper, we'll describe in detail, just briefly describe the definition of these two kinds of corroborative and contributive attributions, and we'll introduce a unified framework in detail for these two kinds of attributions. We'll also talk about some properties and metrics and further future works or directions for this domain. Yeah. So actually, corroborative and contributive attributions are just something we have already been very familiar with. So actually, citation generation or the large language model attribution is just one kind of corroborative attribution. So in the context of corroborative attribution, we are just finding some source to support our statement or claim generated by the large language model. And training data attribution, on the other hand, is a kind of contributive attribution, where we mainly focusing on explaining our model. So a training source could be influential to some certain behavior of our model. So this kind of attribution just want to find such sources that are responsible. So now let's take a look at the diagram here. This diagram just basically describes the unified framework of these two kinds of attribution. It could be applied to both attributions. So basically for both attributions, we'll have one input and we pass it to the large language model we have. And then we'll just have an output from the model, right? So the input and output as a pair, they contribute to something we call the attributable units. And once we have the attributable unit, we'll look up something inside a data set. This data set is called the attribution domain. So in this domain, we want to search for something that is relevant. And we just put each pair of attributable units and a source in the attribution domain into an evaluator. The evaluator is a scoring mechanism. It could be, for example, in the TDA case, the evaluator could be something like the Lee-One algebra training or influence function or tracing. It just gives a score for the pair of claim and your data source. And once you have the score, you could just select something and put them into the attribution set. The attribution set is just the result of your attribution process. So this is a unified framework that works for both kind of, the attributions. And there are actually approximately 6 main components in this framework. They are the input X, output Y, model M, and also the attributable unit Z I talked before, the attribution domain, and the evaluator. So I think the first 3 components are just very trivial, so we'll just skip them. And I will talk about the later 3 in in detail. So the attributable unit is defined as a tuple. The tuple contains actually four elements. The first element is the input, the second element is the output. And the additional two elements are two indices that are indicating where your query actually where are the actually the part of interest in the output, because sometimes we may not be interested in the whole output. We are just maybe curious about a part of the output. And sometimes if the ing they just contain the whole output, sometimes we just use y to denote the attributable unit for shorthand. And I think this is also an ambiguity of notation in the original paper. And after we have defined the attributable unit, we can further define the attributable set. So an attributable set is basically just a set of all possible attributable units, all the pairs of inputs and outputs. And a caveat here is that the attributable set is not equivalent to the attribution set. These are actually two kinds of different terminologies. Attribution set, as I described maybe in the diagram before, it's actually the results of our attribution process, whereas the attributable set is the set of all input and output pairs. Another definition is the definition of attribution domain. So it is just something similar to the source of attribution we discussed in the previous paper. Attribution domain contains multiple sources. These sources could be training instances or maybe just some documents, depending on what kind of domain you are in. And one example is just the large language model training data. And so for this kind of attribution domain, we may focus more on the training data attribution. So the evaluator is actually the key components in the whole attribution system, because it is something like an algorithm that provides a score for you. So an evaluator actually, it takes a look at a pair of, the attributable set and a source from the attribution domain. Basically, you can think these two stuffs are maybe the in the TDA case, it is the training instance and testing instance, and you look at both of them and you will return a score for them, indicates whether they are relevant. So it's the TDA example. Also, there are another example. There is a simple binary evaluator called exact match. So this evaluator returns a true only if there is a exact correspondence inside the source. And one thing I want to mention is also that we also denote the implementations of an evaluator as we had. As you may notice, the evaluators are actually different from their implementations. For example, an evaluator could be something like the counterfactual change of loss by removing one training instance. But their implementation could be a lot. For example, you can implement it with the most direct implementation, the leave out retraining, or maybe something like the PVRF or inference functions. All of those could be called the implementations of an evaluator, but they are not necessarily the evaluator itself, because they could be non-ideal or imperfect. And there are just a few more definitions for attribution set and relevance function. So attribution set, as I mentioned before, is just the result of your attribution process. It is a set of all the pairs that has a score larger than a threshold alpha. And relevance function here is actually just another metric that is estimating the relevancy between each pair. It just returns an additional score. And the higher the score, the better the attribution is. And based on this definition, we can also maybe define something like the R relevant attribution set, which just add another, another requirement that the relevancy should be larger than R. So let's take a look at several evaluators. So the first type of evaluators are the corroborative evaluator. So basically the corroborative evaluators are just binary because either you have support or not support, two cases. So if your source just supports your claim, then you return a 1, otherwise you return a 0. There are a few examples for this kind of evaluator. The first one is the exact match, which we mentioned before. It is a very strict evaluator. And there are also actually two alternatives. One is the valid paraphrase. The paraphrase here means that as long as your source retrieved from the domain could support your claim, then we'll view that as a valid attribution. There could also be something like the textual entailment, which means as long as you could logically derive the claim from your source, then you are okay. There are also something like the contributive evaluators. So this kind of evaluators actually we are more familiar with. It is a continuous evaluator and focuses on some counterfactual effects of removing one training instance. So when we are doing contributive attribution, our attribution domain is usually just the training data. And there are also two types of different counterfactual contributions differing by the effects they are focusing on. So in most of the TDA papers, actually, we are focusing on the effect on the loss of removing one training instance, which we call this kind of evaluator, the CCL, counterfactual contribution to loss. However, there are actually also another kind of evaluator proposed by these authors, which is called the CCO, the counterfactual contribution to outputs. We'll take a look one by one. So the CCL is just something, we know before. We are interested in how the loss will change because of the removal of one training instance, but there are actually some drawback on this kind of evaluator because we are just focusing on the loss. It's just some magical number, but it's not semantic. So when we retrieve something, it may not have some semantic meaning. So some examples of the CCL are just maybe the LOO, leave one out, PVRF, or influence functions, stuff like that. And I want to just focus more on the second type of evaluator called the CCO. And the CCO is actually the counterfactual contribution to output. It is looking at the output behavior of the model. So basically, it does the following thing. Let's assume you have a model and you pass an input to it. You get an output Y, right? So after we do some, leave one out and retraining, assume we have another new model. And we can do the same thing, pass exactly the same input to the model, and we'll get a new output Y prime. So the CCO basically just compares these two versions of outputs. So if your new output no longer agrees with your old output, and then the CCO output, the CCO evaluator will return a 1, which means the training instance is influential. I think it's also very intuitive, right? So and also based on the definition of the agreement here, we can also have different types of CCO evaluator. For example, exact match CCO or textual entailment CCO. Okay. So I have just described about something about the details of the framework and also its components. So I just wonder, does anyone have some question to this point? Uh, if no, we'll just resume. So there are also some properties for the attribution sets, the results provided by your attribution algorithm. So the first, I think the first most important property or metric of attribution set is just the correctness of it, right? So basically, we have a few metrics to evaluate how correct your attributions are. The first one is just the validity. So the validity here means that you are comparing your attribution to a ground truth evaluator. So what are the ground truth evaluators? So let's also use an example in the training data attribution case. So some evaluators that you are more confident with is actually just the ground truth evaluator. For example, a lot of papers just use the leave-one out retraining or the PBRF as the ground truth. So these kind of evaluators are called the ground truth evaluator. And we are also curious about the coverage of our attribution sets. The coverage here basically means the similar thing at the very beginning of our previous paper. So we want to cover most of our claims, which means we don't want to leave out any one of them. Suppose we have 10 claims made by our large language model. We want to find 10 evidences for each of them, right? And there are also some metrics borrowed from retrieval, the precision and recall. So precision here means that your retrieved attribution should be valid, which means your score should be higher than your threshold. And it calculates the proportion of such kind of instances inside your attribution set. And recall is actually defined on one single attributable unit. So suppose we have a ground truth S prime that consists of all the sources in the attribution domain that is actually relevant to your to attributable unit or your claim. Then the recall basically calculates the proportion of the instances that is included in your attribution set. And finally, it's just another one additional property called R-relevancy. So given the relevancy function, you will want your attribution set to have high relevance. You want your relevance to be greater than R. So after talking about the attribution sets, we'll also take a look at the attribution system. As we mentioned before, the evaluator is actually the key components in your attribution system, and it actually determines a lot of the behavior in your system. So for an attribution system, actually what we want is the consistency or the stability, which means you don't want your attribution system could consist of some kind of randomness, but you don't want your results from 2 runs to deviate a lot, right? So the formal definition is the expectation of the distance between two attribution sets, A and A prime, should be less than or equal to epsilon. And the distance here, actually, you have some freedom to define it. For example, you can just pick the Jacob distance, which is the intersection, the number in the intersection divided by the number in the join. Also, another property of an attribution system is the efficiency. So which means you just want your system to be it doesn't cost a lot of time and space. Let's take a look at a few use cases of these two kinds of attributions. So for the corroborative case, apparently it could be applied to question answering, as we discussed a lot in the LLM paper. You could retrieve something from a trustworthy source and improve the accuracy of your answering. And another application is just the fact checking. You want to improve the trustworthiness of your claim, and you want to check it against some facts. So for the contributive attribution, actually the use cases are more interesting. So the first use case is the author compensation. As you all know, today's large generative models actually relies a lot on the training instances that comes from some human authors' work, right? So such human authors' work may have some license, and in order to recognize the effort or the contribution of these human authors, the contributive attributions can actually look into the training instances and see which of them are actually contributing to the success of the generative model. So by doing so, we could just compensate the authors afterwards. And another thing is about maybe the privacy. There is a compliance called the GDPR, the General Data Protection Regulation. So sometimes we don't want to see more data. Instead, we want to get rid of the effects of some data. We want to unlearn them. But actually, it is very, very challenging. And also sometimes you are not sure whether the influence of these sensitive data, whether the sensitive data's influence are still there. So one way to make sure the influence are removed is that you just apply the contributive attribution method to the model and see whether the sensitive data doesn't have any influence. Okay, now we also come to the future direction section. So there are actually a few potential promising directions proposed by these authors. So the first direction is the counterfactual contribution to output evaluators. As we discussed before, this kind of evaluator is actually a new kind of evaluator proposed by these authors. So these evaluators are not developed or investigated so much as the CCL evaluator. And they have some benefits, they have some merits because they are semantically meaningful compared to other contributive attribution evaluators. So this is one potential direction. And another direction is just what we have discussed a lot in the previous meetings, which is just scaling up the TDA for larger models. And finally, another direction is something called the hybrid attribution systems, which means you want to combine the two kinds of attribution methods, the contributive and corroborative ones, because some of the tasks may require the ability to incorporate both kinds of attribution. For example, the fact tracing is just one such task. It is looking at the training data set and see whether there are any factual evidence for the query set. And when doing this kind of task, you may not only because this kind of task is actually model specific, right? You want to explain the behavior of your model, but you also want to retrieve some meaningful uh, semantic attributions. So this kind of task is actually a mix of both, I would say. And Qirun will also introduce one data set on this kind of task called F-trace, and in the later part, yeah. So that's all about the unified framework paper. Uh, so are there any? So after I introduce maybe the properties or the directions, future directions, are there any new questions on this paper? Okay, if still there are no questions, I'll just speed up and finish the final paper. Yeah. So this paper is actually called the Attributing Learned Concepts in Neural Network to Training Data. So it is actually doing one thing. It is applying a TDA method track to a special case, the concept probing. So it is not applying to the model, but the probe. So the diagram here shows the main experiment procedure of their paper. And so I'll just first discuss about some backgrounds for the probing part, because I don't remember we have discussed this probing in our previous meeting. And so for probing, actually, what we'll have one base model called fx, and we denote the first I layers of this model as f less than or equal to I. And then we'll have a linear probe, G. So a linear probe is just a linear classifier or maybe logistic regression classifier. And we'll just attach this probe G to the output end of our first I layer. And we'll have the structure called the subnetwork plus probe. And this is about the models. And for data, suppose we have a concept C. So the concept C could be anything, actually. It could be something like an objective, and an objective such as a dog or a cat. So we are doing image classification here. So if our image has a dog or cat on it, we will say that this image is actually with the concept, and vice versa. So the probing process is actually just to train our base model F on the training data set called XTrain, and test it on validation data set called XVal. And after doing so, we will continue to train our probe. So basically, we will first re-annotate our data set. For example, for the image set with our concept, we'll just annotate the label as one, and for those who didn't have, and we'll just label them as 0. So after relabeling our data set, we'll train our subnetwork plus probe on this re-annotated data set. But basically, we will have our first I layers frozen, and we are only training the classifier, because we don't want to change the embeddings anymore. And by doing so, we'll then just proceed to validation, and validation it on another re-annotated validation data set. So if suppose we have a high accuracy on the validation set, then we may conclude that our model have learned certain concept in the first I layer. And I also want to introduce something further than basic probe, which is called the sparse probing, because the authors in this paper just use this technique. And this sparse probing is actually just adding one limitation to the normal probe. So first we have to define the CAV, the concept activation vector. So this vector is actually just a normal vector perpendicular to the decision boundary of your linear classifier, as shown here, and it is pointing towards the with concept side of the embedding space. And so the K-sparse probing is basically just adding one additional limitation. It is requiring that at most K elements of the CAV related to a classifier are non-zero, which in other words means that you could only use at most K neurons or K dimensions in the embedding in your prediction. So by doing so, actually, it allows for more interpretable concept directions. And so after talking about the backgrounds, we can just introduce the basic experimental setup of this paper. So basically, the authors use the ImageNet 10P dataset with the model ResNet 18. And the model achieved 45% top-line accuracy on this setting. And the authors also chose two kind of concepts. One is just a concrete concept called, which is snake and object. As long as the image has a snake in it, it is with this concept. And sorry, another kind of another concept the authors select is actually a more abstract concept called the hydrospatial frequencies. It's actually a property of an image, and I don't think it could be really understood by human eyes. But anyway, some deep learning models are really good at distinguish this kind of features. So the authors just use the Inception V1 model to detect this image and select the top 0.001% highest activating images as the instances with the concept. After defining the concepts and selecting the model and dataset, they just apply the probing steps, and finally they just applied the training data attribution to the probe. So that parts are just very simple. So before we proceed to the results of this paper, I just want to know if are there any question on the experiment setup or maybe the background?
I do have one question.
Yeah. Please go ahead.
If I understand this correctly,
Mm.
for the probe, I think the accuracy here is kind of weird to me because we're essentially doing like binary classification, right?
Yeah.
And why is it like only 45% if it can flipped?
Actually, the 45% accuracy is not for the validation accuracy. It's just for the classification accuracy on the original data set of ImageNet 10P. So there is actually not a it's actually not doing a binary classification here. So for the validation, for the concept learning binary classification accuracy, I'll just introduce them maybe in in the next few slides. Yeah.
Okay. Thanks. I see.
Yeah. No problem. Yeah. Okay. So actually, are there any questions before we move on? If there are no such questions, I just briefly introduce the results in this paper, which I think are very interesting. So this is just something. Yeah, we just talk about the the real concept detection accuracy, the binary classification accuracy. So actually they are not pretty high, around above the 70% and close to 90%. And actually there are different patterns or different trends for two different kinds of concepts. So for the first abstract concept, the high-low frequency, actually it has a inverse U-shape, right? So actually the intermediate layers are more good at distinguish such kind of concept. While on the other hand, the snake concept, the more concrete concept, the later layers does better on this classification task, which is also reasonable because the ResNet model is just designed or trained to do the classification, so it is just trained to distinguish between what images are showing snakes and what images are showing other objectives, right? So these are the results on the probing accuracy. So the results here show that actually the probe has learned something about the concept, and then the authors just proceed to the TDA, the training data attribution for the probe. Actually, there are 4 images here, and we just look at the first 2 images on the left here. So the first 2 images, it actually is plotting the attribution score against the rankings of the training instances. So there are actually 2 observations in these two diagrams. So the first observation is that for different layers, actually the attribution scores are pretty close to each other, which means the layer actually does not affect the probing very much. So, and another observation is actually that, so except for the least influential instances, these other training instances, maybe the first 10,000 training instances, they all have a very similar attribution score, which means we couldn't really see some very influential points or instances in training set. And we can also take a look at the 2 images on the right here. These 2 images basically shows the retraining results. So the authors, they just remove the top 100 or 1,000 or 10,000 influential instances from the training data, and they retrain the model. Then they do the similar process evaluating the accuracy on the validation set. And their discovery is that no matter how many training instances you remove, the accuracies here are actually also very close to each other. And you may also see the confidence intervals here in the graph in the left. You may discover that these confidence intervals all overlaps with each other. So the conclusions we could draw from this experiment is that actually the learning of a concept is a more diffuse process among all the training instances, instead of just depending on a few top influential instances. So that's I think, the key takeaway from this paper. And here are just some additional results the authors show on the validation accuracy and probe sparsity. They want to see whether the selection of probe sparsity will affect the accuracy. So the conclusion is just as you increase K, your accuracy will just increase because you are utilizing more information, right? But no, actually for a different case, the relative ranking of different layers it actually is very similar to each other. Yeah. Finally, the authors also take a look at how the probe sparsity affects the attribution. So they take out the highest attributed four highest attributed instances and the two lowest attributed instances. And as you can see on the left here for the snake concept, actually for the highest attributed instances, except for the order, the relative orders, these four instances are still the same. And also for maybe the high-low frequency concept, except for the k=1 case, no matter for k=25 or k=100, the retrieved instances are exactly the same. So actually, their conclusion is that attribution results do not vary a lot between, even if you differing the probes. Yeah, so these are just all the results they have presented in their paper. And they also just realized some limitations of their paper. There are actually three main limitations. The first one is that they haven't tried other models, they just use the ResNet 18. And another limitation is that actually they could potentially try another modality. You could also do some LLM probing, which is also very interesting. And finally, they only use the track method for attribution calculation. Maybe it is also important to make sure whether other TDA method will yield the similar results. So these are the limitations realized by the authors. And I think that's all for my part. Finally, are there any questions on any parts of my part? If no, I'll just I think I'm just a bit over time. I'll just hand over to Qirun. Yeah, Qirun.
Thank you, Shixuan. Right. So now I will just start to begin my part. So my part covers two papers. The first is about a benchmark called fact tracing, and the second is about a survey on fact knowledge probing. So let's first take a brief review of the corroborative and contributive attribution framework introduced by Shixuan previously, which we'll term in later sections as CCA framework. So the two papers that we'll cover will also be unified in this framework. So the first kind of attribution is called corroborative or confirmative. It focuses on kind of external validity, which means it wants to verify the truthfulness of model outputs using an external corpus that need not be in the training data. And the second kind of attribution is called contributive attribution, which should also be causal, which means it focuses on internal validity, which means it identifies influential training data that lead the model to generate specific outputs. So the first paper is called fact tracing. I would like to make a new title for this paper instead of using its original title, because I think this new title may better show how it can be unified in our CCA framework. So the new title is How to Benchmark Contributive Attribution Methods for Identifying Corroborative Training Sources. So let's first take a look at the problem statement. So the definition of fact tracing is how to identify which training examples or proponents taught a language model to generate a particular factual assertion. And our specific evaluation target is the TDA methods. So please note that we are not evaluating the language model, but we are only evaluating those TDA methods. And the two kinds of TDA methods include gradient-based methods and embedding-based methods. And thirdly, the significance of fact tracing is about two parts, both contributive and corroborative. So fact tracing not only focuses on the question of where the language model learned the factual knowledge it outputs, but it also asks the question of whether the output fact is true. So before we dive into the details of the dataset, let's first take a look at a simple example of how fact tracing actually works. So there are two sets. The first is a query set. And the other is a kind of attribution set. The query set contains many queries, and the language model reads a query and outputs a prediction that may answer the question is query. So in this process, the language model's internal states on this query is also recorded for the later use of TDA methods. So our task is to use a TDA method to score all the training examples in the attribution set. The higher the attribution score is, the more likely this TDA method thinks that this candidate example accounts for the language model's specific output, which is 7076 in this case. And after obtaining the TDA score for each example in the attribution set, we will do something similar to a traditional information retrieval framework, which means we will retrieve the top K candidates in the attribution set according to their TDA scores, and then evaluate this TDA method using some traditional metrics like precision or recall. Okay, so about what I've just introduced, is there any question? Or can you hear me clearly or clearly view the things that I'm presenting? If yes, then let's just proceed. Okay, so before we start to introduce some details of data structure, we may first introduce some key challenges in fact tracing evaluation. So the first challenge that obstacles the progress in this direction is that how we can obtain ground truth labels regarding which presenting example can truly account for a language model's prediction, given the large size of the pre-training corpora. And secondly, how we can overcome the computational burden of traditional TDA methods so that we can evaluate them, especially on large language models in large datasets. So these two methods are the main obstacles that limit the past research on the fact tracing of large pre-trained language models. And they're exactly the main technical contributions of the paper that I'm introducing. Okay, so now let's proceed into how the dataset is curated. So this benchmark contains two datasets. The first is called ftrace tracks, which uses real facts derived from the tracks dataset. Please note that tracks is a very old dataset, which contains Wikipedia abstracts and corresponding fact triples. But apart from this real fact dataset, the authors also think it necessary to curate another fully synthesized dataset using made-up entities and relations. And I will detail the reason why such a kind of synthesized dataset is necessary. And for each dataset, there is a kind of attribution and query split as is introduced in my previous example. The attribution set is formally defined as all the language model training examples that might be considered proponents. And the query set is defined as the test examples, each annotated with their ground truth proponents from the attribution set. So let's first take a look at the structure and terminology of the real fact dataset, ftrace tracks. So this dataset contains quite a few nuanced details, and I will try to cover them one by one. But if there is anything that doesn't seem make sense to you, please feel free to raise questions at any time. So both the ftrace tracks dataset is actually curated from two existing old datasets. The first is called tracks, and the other is called llama. Tracks is used to curate the training set, while llama is used to curate the query set. So let's first take a look at how we can convert tracks data into the training examples of ftrace tracks. So both the tracks and llama dataset uses the same hierarchy from abstract to sentence to fact. So we can first take a look at the section A in this figure here. This is an example of a tracks data point. It contains an abstract of an introduction to Rabobank. And in this abstract, there are multiple sentences. And this abstract is associated with many facts. As can listed above, there are altogether 5 facts associated with this abstract. And each sentence in this abstract is also associated with their corresponding facts. So the fact is defined as a kind of Wikidata triple. So the first element in the fact triple is predicate, which is like take the F1 for example, then the predicate is just country. And the second and third element in this triple is just the object and subject. So in the fact example, F1, the subject is just the Rabobank and the object is just Netherlands. And their relation is just Rabobank's country is Netherlands. Okay, so we have now finished introducing the structure of the original tracks dataset. Now let's take a look at how to convert it into the training examples in ftrace tracks. To put it simply, each example in ftrace tracks training dataset is a track sentence. But instead of using the raw sentence, we need to mask out either the subject or the object of one of the facts in the original track sentence. So we still use this figure as an example and still use the first sentence in this abstract, which is Rabobank is a Dutch multinational, blah, 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 until the Netherlands. So we use this sentence example and we want to convert it to a training example. How we can convert that? So if we can see that this sentence involves 3 different facts, which is F1, F2, and F3. And if we want to target F1 and mask out the subject in F1, then we just mask out the Rabobank that is contained in this sentence and thus obtain the first row in, contain the second row in the section B of this figure, where the word Rabobank, which is the subject, is already masked out. And this kind of clause is just employed as an example for training. So this is how we can convert the original tracks data into a training example of our new dataset ftrace tracks. So now let's proceed to look at how we can obtain a query. The query is obtained in a very similar way from the original Llama dataset. So the original data in Llama is a bit simpler than tracks in that it only contains sentence and fact, but no abstract. Each data in Llama is formatted as a QA format, where each question is a kind of closed question, and it will also be provided with a corresponding answer and the fact triple that should be used to answer this question. So in order to obtain a query for our ftrace tracks, we can directly use the Q&A data point from the Llama and also mask out the corresponding subject or object of fact for the prediction. Please note that both tracks and Llama use the same source for their fact triples because the fact triples are both sourced from the Wikidata triples. So it is naturally easy to annotate the ground truth proponents for each Llama query in the tracks dataset. And the proponent is just defined as those examples that we convert from tracks that express the same fact as the Llama query. Let's still take the figure as an example. So for the section C, this Llama query, it involves the fact F2. So we just want to find in our training examples, which is section B, on what examples in this section contains the F2 fact. And we find that in a very easy way that the second row or the second example contains the F2 fact. And so it should be annotated as a ground truth proponent for this query. So this is the annotation process of both the query and training or attribution set of our ftrace tracks dataset. And lastly, I want to introduce an important point of the annotation process. It's about sentence level retrieval, which means, as was introduced above, each example in our training dataset is originated from a track sentence. But depending on what fact we pick and whether the subject or the object is masked out, we can obtain a number of different training examples from the same track sentence. So when doing retrieval, should we consider the examples that is originated from the same track sentence as the ground or as the ground truth proponent for a llama query? And the answer is yes, because although two examples, they originate from the same track sentence with different maskings, they express the same information in text. So the final retrieval target should be sentence level instead of masking level. And the same track sentence with different maskings should all be considered true proponents. So this is all of the structure and terminology of the F-trace tracks dataset. Is there any questions? If no, then just proceed. So after introducing the real fact dataset, F-trace tracks, we will continue to introduce the synthesized dataset, F-trace stings. So before we dive into the details of the dataset, we first ask the question, why we want a synthesized dataset? This is because there are two negative factors that can greatly affect the TDA method's performance on real fact datasets. So the first factor is called saturation, which means a fact is already known by the pre-trained language model. So if this condition is met, then during tuning, there will not be any learning signal for those tracks examples that contain this fact. And this will further lead to the fact that those examples will definitely not be detected by TDA methods, because TDA methods need to leverage the language model's internal states during training to identify or detect the relevant examples. So this kind of phenomenon is termed as saturation, and it will negatively impact the TDA method's performance. And the second factor is called lexical overlap. It is a bit easier to understand. It's just because if we use real facts, and since the tracks examples and the llama queries, they naturally have surface form overlap since they are both mined from Wikipedia, then it will definitely favor those information retrieval baselines such as BM25. So these two factors will downgrade the performance of traditional TDA methods, but upgrade the performance of information retrieval baselines, and will thus make the evaluation results not precise. So that's the reason why we have to make another fully synthesized dataset. So for the curation of F-things, its format and relation is quite similar to what is shown in F-trace tracks. The only difference is that it replaced original real entities with some human made-up entities, such as the entities listed in the right-hand side figure. And about the statistics of these two datasets, we can see that due to the reason I mentioned before, one sentence in the original tracks dataset can derive multiple different training examples with different maskings in our F-trace tracks. So in the statistics, the average number of proponents for a given query is 83 and 62 for F-tracks and F-things respectively. Okay, so now let's proceed into the evaluation setup of the TDA methods. So I divide this part into two different segments. The first is about some basic evaluation setups, and the second is about some specific noteworthy points that are like specific to the evaluation of TDA methods in our scenario. So let's first take a look at the basics part. So what TDA methods or baselines we want to evaluate on? The answer is simple. We evaluate two TDA methods. One is gradient-based, and the other is embedding-based. And in order to compare with some traditional information retrieval baseline, we also include the performance of BM25+, which is an upgraded version of traditional BM25. So the gradient-based method is track-in. I will not go into mathematical details of it, but its principle is just derived from using the loss gradient of a query and a training example, and they just perform a kind of cosine similarity between their loss gradient and accumulate this cosine similarity across multiple checkpoints. And for the embedding-based method, it's much easier to understand. It's a kind of using the layer outputs of a language model as the representation for the calculation of cosine similarity. Okay, so now let's take a look at what evaluation metrics we're gonna use. We use two evaluation metrics, which are both traditional information retrieval metrics. The first is recall at 10, which means we'll calculate the kind of quotient of the number of correct proponents in top 10 retrieved results compared with number of all correct proponents in the attribution set. And the second metric is called mean reciprocal rank, or simplified as MRR. And in its expression, the rank Q notation means that the rank of the first true proponent for each query Q in the whole query set, big Q. So as you can see, if we can perform perfect retrieval, which means for each query, small q, rank Q is always 1, then the perfect value for MRR is just 1. So MRR is a value that is between 0 and 1. Okay, so let's go ahead to take a look at what language model and checkpoints we're going to use. As I mentioned earlier, we are not evaluating language models, but only evaluating TDA methods. So the language model is fixed as a MT5 base model, which is a multilingual version of T5 with 580 million parameters. The pre-training data for this model is MC4. And since this pre-training data includes all of the Wikipedia, this means that this pre-trained model already knows some facts in our real fact dataset, ftrace tracks. And this actually justifies the creation of another synthesized dataset, right? And the author did an initial evaluation by using both the pre-trained and fine-tuned checkpoints of this language model and test their performance on the two different datasets. And we find that, well, before fine-tuning on ftrace tracks, the pre-trained model already has a kind of 24.3 performance on this real dataset. So this means that the pre-trained transformer indeed understands some of the factual knowledge of the real fact dataset we curated. And after fine-tuning, this performance increases to 47.4. But for the synthesized dataset, we can find that before fine-tuning on this dataset specifically, the pre-trained model's performance is 0, which means this dataset does not contain any knowledge that is already known to language model before fine-tuning. But after fine-tuning, the performance just surged to 81.0. So this is the model and this performance and knowledge like management on these two different datasets. And about the checkpoints we like to use, we need like multiple checkpoints because many traditional TDA methods need an ensemble of different checkpoints in order to make their final results stable. Especially for those gradient-based methods track in, it needs to choose 3 checkpoints. And in order to cover significant parts of training, the 3 checkpoints it chooses is uniformly spaced out in terms of training loss. And for embedding-based methods, we just simply use the final checkpoints representations. Okay, so let's finally talk about some special evaluation setups. So the special setup mainly revolves around 2 questions. The first question is just one of the main technical challenges that I mentioned earlier. It's just how we can make the evaluation of TDA methods computationally trackable in large scale. Well, the author's solution is illustrated in this way. Instead of scoring all the attribution set or all the training set, we only score a carefully selected subset for each query, Z query. So how is this carefully selected subset chosen? Well, firstly, it should contain all true proponents for Z query, since we need to ensure that the model has the opportunity to retrieve all the proponents. And secondly, we need also to include the top 100 retrievals from BM25 for this query in order to see if the TDA methods will be severely biased by merely lexical similarity. And thirdly, we also include 100 examples that share the same prediction target as Z query into this selected subset. So this choice is originated from an observation that traditional TDA methods tend to retrieve examples with exactly the same output as the query. So including this slice will help us test if the TDA methods will be preferentially confused by those examples that share the same prediction target. Then finally, we will include 100 randomly selected examples. So as we can see, for each query, the carefully selected subset is only about a bit over 300. Its size is only a bit over 300. So it greatly reduces the computational burden. And about the second question, how to reduce the impact of saturation on certain non-queries, the authors conducted another solution, which they term as they only evaluate on purely novel facts. So how is purely novel facts defined? Well, the purely novel facts is just defined as the queries that the language model failed before fine-tuning, but succeeded afterwards. And the authors just extract out this subset and call it fine-tuned learned and evaluate the further language models and evaluate the TDA model's performance only on this subset of queries. Okay, so we are finished with the evaluation setup. Is there any questions? If no, we just proceed to take a look at the evaluation results. So the main results is just aggregated in these two tables. The table 1 is on the real fact dataset, ftrace tracks. And on this real fact dataset, since the pre-training auto already masters a certain amount of knowledge, we can use both pre-trained and fine-tuned checkpoints to evaluate the performance of TDA methods. And the second figure below is on the synthesized fact dataset. Since the pre-trained language model cannot achieve any accuracy on this synthesized dataset, we can only use the fine-tuned checkpoints to evaluate the TDA methods. And something noteworthy in the methods column include a random target label. So the random target is another baseline apart from BM25. It outputs a score of 1 for all the training examples with the same output label. So this is another kind of sanity check that whether our TDA methods are doing anything more than just simply matching the query's output label. And apart from the introduction of this additional baseline, let's take a look at these results. So let's first take a look at the ftrace tracks. For this dataset with real facts, some interesting observations include BM25 outperforms all other neural TDA methods by a large margin. And to our surprise, the gradient-based method track-in, it only slightly outperforms embedding-based methods for pre-trained model, but significantly underperforms embedding methods for the fine-tuned models. So this is really weird, right? But when we switch to the performance results on the table 2 of the synthesized dataset, we found that, okay, it seems much more normal here because all the neural TDA methods outperform BM25, and the more computationally heavy gradient-based method track-in also outperforms embed. So why is that? Well, the reason is indeed or exactly correlated to the phenomenon of saturation that we introduced in earlier sections. So because when we switch from the real fact dataset to the synthesized dataset, we did two things. First, we controlled the lexical overlap between queries and candidate examples. And in this way, neural TDA methods beat BM25. And secondly, we also mitigate the model's performance saturation on test queries. And this exactly accounts for why the gradient-based method track-in, when applied to fine-tune checkpoints, finally beats the embedding-based method in the ftrace sense. So is there any questions on my analysis of the evaluation results? If not, just proceed. Sorry, we may exceed a bit of a time limit, and I will try to finish the remaining results in 15 minutes. So thank you for your patience. So the two tables in the previous page are some number results. And I would present another two results. Then these results, they do not evaluate what TDA method works better, but instead, they evaluate what kind of hyperparameter configuration works best for one TDA method. And as you can see in this grand figure, it actually wants to explore what model layer, when used for calculating TDA, is producing the best performance. So the takeaway is, for embedding-based method, the output of the first embedding layer actually works best. And for the gradient-based tracking method, it is also the embedding layer that works best. But for the embedding-based method, the embedding layer or the output of embedding layer only contains or mostly contains the lexical similarity. But for gradient-based method, although we also find the embedding layer works best, we can think that the embedding layer, in this case, it includes contextual information, since we need gradient information, and gradient signals should backpropagate through the model. And that's the reason why the embedding layer for the tracking method should also contain some contextual information apart from purely lexical similarity. Okay, so now let's take a look at some other hyperparameter choices for the gradient-based method specifically. And as is illustrated in this table, some key takeaways include, firstly, the gradients, when rescaled by eta factor accumulators, work consistently and significantly well when there are no such eta factor. This should be because that when including eta factor accumulators, the TDA method is approximating the true parameter updates that was employed during training process using Adam optimizer in a more precise way. And second takeaway is that the unit normalized gradients, which means cosine similarity, also works much more better than unnormalized naive dot product. So this might be related to some lens bias that has long been a non-issue in traditional TDA methods, which is just that some TDA methods without normalization may tend to only pick short sentences over long, or pick only long sentences over short. And the third takeaway is that the ensemble of multiple checkpoints can sometimes be outperformed by single bad checkpoint, but there is no obvious or consistent phenomenon on this issue. Okay, so we are now finished with the first paper about how to benchmark different TDA methods for corroborative training sources. But now let's take a look at the final paper. So for the final paper, it talks another interesting topic termed as factual knowledge probing. So in my opinion, factual knowledge probing is actually not very related to the grand scope of data attribution. It's kind of a topic beyond the CCA framework introduced previously by Shixuan. So I will just quickly go through this paper since it's not very much correlated with the general topic of our reading group. So the first is still about the problem statement. So what is factual knowledge probing? It's actually about quantifying the type and amount of factual knowledge present in pre-trained language models. So please note that we are only focusing on pre-trained language models instead of fine-tuned ones. And the only data source that we want to validate upon is just the pre-training corpora. And for a complete factual knowledge probing framework, there are two major components. The first is just the pre-trained language model. And second is a data set of truthful facts. So for the facts in this data set, we want them to be the specific facts that we want to extract from the pre-trained language model. Since this data set is more like the evaluation data set. And secondly, we want these facts to be truthful, since in order to evaluate the extracted answers that we obtain from the language model, we definitely need some ground truth answers to compare with. And thirdly, the format of this data set are mostly some relations between subjects and objects generated from certain template. So before we dive into or go through some classical papers in factual knowledge probing, let me first address the importance of factual knowledge probing. So the importance is mainly like two branch, but for this paper or this survey, it mainly covers the methods covered in this paper mainly focus on the right-hand side, which means that they want to use pre-trained language models as knowledge bases for extracting relational knowledge. And this application can eliminate the use of traditional complex pipeline for knowledge extraction and also eliminate the need for label training data. But a normal problem in this direction is just about the factuality. So the coverage of this survey on factual knowledge probing is the papers that cite a groundbreaking paper called Language Models as Knowledge Bases. They only focus on those papers that directly cite this paper. And in this famous paper, it first introduced the concept of pre-trained language models as knowledge bases. And the structure of this survey is quite clear. It ranges from the methods for factual probing to what data can be used for factual probing, and proceed to talk about two key points in the effectiveness of factual probing. And finally, propose some obstacles in the future directions that can improve the effectiveness of factual knowledge probing. So I will quickly go through the methods for factual knowledge probing. It is organized in like 3 layers, which respectively talk about how to optimize inputs, optimize pre-trained language models, and optimize the outputs in order to improve the factuality of the probed data. And for this part, actually, I think it like cited much from another famous survey on some prompting and probing methods in natural language processing, which I listed here for your reference. So when it comes to probing inputs, it classified this category into 2 subcategories. The first is those non-optimized inputs, which means, okay, the probing input tags are not further altered, and we just create a specific format for the inputs or for the input prompts and just directly send them to a language model without modifying or ensembling them further. So for the format of input prompts, we have 3 categories ranging from clause to QAs and to like entities. And for the second kind of subcategory of probing inputs, we need to directly optimize the inputs, whether in the discrete level by manipulating different tokens in a discrete way, or in a concrete level by manipulating the latent representation of these tokens or input prompts. So I listed 2 examples here. On the right-hand side, the example is just a good exemplification of how we can mine and paraphrase prompts to create like a bunch of alternative ensemble prompts. And in the figure in the like bottom down of this page, it's just an exemplification of how direct optimization in the continuous space works. Before you, apart in this figure, instead of directly using the LM embedding outputs as the input to the pre-trained LM, we insert a layer of adapter, and we hope that this inserted adapter layer can help to make the input prompt being less sensitive to the language model, so that it can reduce the sensitivity problem of the language model against input. So the previous section is about how we can optimize inputs in order to improve the factuality and robustness of factual knowledge probing. And the second section is just about how we can adapt pre-trained language models to improve the knowledge probing process. And I think this process is also quite clear. We just have two different approaches. The first is supervised fine-tuning, and the second is self-supervised fine-tuning. And inside self-supervised fine-tuning, I think contrastive learning is used most frequently. So I think we are all familiar with these methods. I just skip it. So the third direction is about how we can manipulate outputs of the pre-trained language models. And the reason why we need to manipulate outputs, or an important reason of why we need to do so, is that we need to debias the output of language model. Because as is shown in this figure and in this famous paper called Calibrate Before Use, the authors show that when we change the majority label and recency of different in-context examples, the GPT-3's performance on the final task will also have great changes. This exactly indicates the perturbations in context examples will greatly influence the final performance of the language model. So in this way, when we obtain the output of the final language model, we should perform some debiasing to eliminate the potential sensitivity to the input context. And the debiasing procedure is also quite simple. We just first detect the bias and then adapt the output probabilities and hope that this procedure can correct the bias. So, okay, now let's move into the dataset that can be used for factual probing. This paper classifies the datasets into 3 different categories, ranging from general knowledge to domain-specific knowledge to other aspects. And I listed some datasets that might be familiar to you, also to me. Like for closed prompts, there are llama that I just introduced to curate the ftrace tracks in the previous paper. And for QA datasets, things like trivia QA, squad, and entity questions are also famous datasets. And for domain-specific datasets, I think MetaQA is a really good example. And for datasets for other aspects, I think some interesting research focuses on how we can update knowledge in PLMs and just create some like temporal relation sensitive dataset. So finally, let's talk about some insights about 2 key points in factual probing. The first is the factors that affect the knowledge retention, the factual knowledge retention of language models. So the paper narrowed down the factors to 3 aspects: the model architecture, the pre-training objective, and the pre-training data composition. And it cites mainly 2 papers. The major takeaway is if we pre-train with some specific objective, then we can definitely help the language model absorb 4 facts. And it is also noteworthy that the recency and frequency of pre-training data are essential for knowledge retention. So as you can see in this left-hand side figure, only when we scale up the number of relevant pre-training documents to a certain scale can the final QA performance of language model achieve a certain level. So this means that only scaling up model sizes without paying attention to the pre-training dataset corpora is not sufficient. And the second question or key point is about whether the prompt should be optimized. It actually originates from a doubt that the improvement from the optimized prompts is actually due to the optimized prompts contains new knowledge, not because they have some conceptually superior property. So for future work, the author proposed that future evaluation should take both pre-training corpora and facts distribution in the probing set or the evaluation set into account in order to make the evaluation more fair and to reduce the chances that it's indeed because the optimized prompts leaking new logic that brings about improved performance. And the second direction for future work is that we can adapt prompt optimization to produce more interpretable prompts rather than only find prompts with merely better performance. So finally, let's talk about a bit about the obstacles to adopting language models and knowledge bases, also the future directions. The author's mainly classifies the obstacles into 3 categories, from consistency to interpretability to knowledge updating. And I think interpretability has been extensively covered in contributive attribution part by Shixuan, and it's just what traditional TDA methods excel at. And for consistency, it points out an interesting observation that language models are highly sensitive to variations in input queries, especially in non-English languages. So maybe working on this direction can produce some interesting work. And the third part is about knowledge editing or adaptation. And the author thinks that we can either locate some modules in the language model that are responsible for factual prediction, or to introduce some additional parameters like an adapter or some LoRa adapters with specific targets and scale them up to really large language models in order to make the knowledge editing effect visible. And beyond this model-centric approach, the authors also propose a kind of data-centric approach, which means they can encode facts with timestamps into the pre-training data of language model so that the language model can be more time-aware. So these are like model-centric and data-centric, the 2 different aspects for improved knowledge update of language models. And I think that's all for my presentation, and thank you for hearing.